I mean, we can try to use our wetware neural networks to do some kind of pattern recognition to try and figure out what might be different. I think we're probably going to fail at that. And then you might also ask yourself, like, how on earth would we decide which one was better?
We're good.
Okay.
Just now.
Good.
I don't know if you want to start from like...
I think it's okay. Yeah, we'll just continue on. And so, like broadly in the field of generative modeling, I think it's an interesting and important topic of how we evaluate these models. And if you want to have a competition that's not judged, and you want to have a leaderboard, you're going to have to do that mathematically. And so we'll talk about that in today's presentation. And we didn't just come here for the very good dogs. Sorry, now the video doesn't know the joke, but that's okay. We also came here for the glitchy dogs. And actually, you've already seen these dogs. These were dogs on the previous slides. But it's always fun to see the failure cases. I think, sometimes the basic dog topology of having one butt and one head gets broken. And so there's fun to be had. Right, so this is the competition page. Just for the quick basic stats about it, they had almost 1,000 participants. Pretty recent, 5 months ago, means that all these techniques should be pretty up to date. There was a token prize money, but don't join Kaggle because of the prize money. And so that's that. Okay, so this isn't just about generating dogs. It's about generating like what kinds of dogs. And the answer is dogs from the Stanford dog dataset. So this was the dataset that was made available by Kaggle for the competition. Here are some samples of that data. I just pulled this out of somebody's kernel. And so you can see that these are like photos of dogs in like various contexts. We know their breed, and we also have a bounding box that tells us kind of where in the image the dog is. And so the idea is that from this data set, you would train your dog generator. Here are some more examples that I pulled randomly out of the data. We can see there's a fair amount of variation going on here. This isn't like we lined up a bunch of dogs to have nice standard headshots. I mean, they're in all kinds of positions, and these are not cherry-picked in any way. I think these are like the first 5 when I opened the Boxer folder. And then these are like, I think maybe I did cherry-pick these ones from the Chihuahua, but they're not like that exotic. There's a huge amount of variation in here. Right, and so today, I'm going to talk about generative adversarial networks. I'm not going to talk about convolutions. We're going to stay away from a lot of the details about neural networks, actually, so that we can talk about specifically this domain. I'm hoping to provide some interesting intuitions to people who are maybe new to this topic. I'm also hoping to tease people who know a bit more about it with some interesting thoughts. We're going to talk about Gann evaluation. Like I alluded to a moment ago, we'll look at the winning solution, and there's probably going to be some dogs. That seems likely, somewhere in here. So, right, generative adversarial networks. We're going to have a few different angles on this because I think there's different ways you can think about it, and I think they're all interesting. This is kind of like the typical image that people plagiarize from the internet when they want to talk about GANs. And I did the same, and I think I did it from someone who did and didn't cite their sources, but I wasn't going to chase that down. So here's one of the narratives about what's going on with generative adversarial networks. The idea is that you have 2 networks, a generator and a discriminator, and they're in competition. And so the idea is the generator is attempting to create realistic images that will fool the discriminator, and the discriminator is attempting to tell the difference between a real and a fake image. And so the idea is that they can learn from each other, and the better the discriminator gets at like determining the difference, and then the better the generator gets at fooling it, eventually you get like a perfect generator, something that creates fake dogs that are indistinguishable from real dogs. That's the idea. And then in this diagram there's the random stuff on the left. So the idea is that we're going to take some kind of randomness, in this case like random noise, and in this diagram the generator takes that and blows it up into an MNIST digit. So this is like an 8, a fake 8, and then we have some kind of collection of real digits, MNIST digits, and then those go in this sort of training regime to the discriminator. And the idea is that like it's a bit, it's an arms race between the two, but we win in the end because we want a good generator. That's one of the stories that go here. If you've heard anything about these before, you've probably heard that story. Hope that's fine. We're not going to go through this in detail, but I just want to make this a little concrete. So we had like winning solutions using this big Gann, which is a fairly recent paper generator. And again, if you don't know about neural network architectures, this is just going to go by in a blur, but like I said, we're not going to dwell on it. So this is what big Gann looks like. So up here, we begin with this random noise and some class. It goes through a series of residual blocks that involve an upsampling. We repeat aspects of the class and latent vector in, and eventually we get an image out of the end. And if you wanted to know what these look like, they look like this. And then they have this these other residual blocks that they use in the discriminator. Generators and discriminators are doing like fundamentally opposite things. One sec, where the generator is essentially blowing up images gradually, and discriminators are trying to collapse them down to a decision about real or fake. Kenneth, you had your hand up, and then we'll go to Matt.
Yeah, so that block, the non-local, what's that? Is it a new one? Non-local. That's the third one.
I actually have no idea what that is.
Okay.
Yeah. That was my question. Okay, yeah. I think what I'd like people to appreciate is that there's a lot of complexity under here, for sure. And we don't need to know it, and I don't know it. I don't know what non-local means. But it gives you some idea of what might be going on inside those little blocks in my previous diagram. Right, and so when people want to be mathematical instead of anthropomorphizing, wherein previously we were treating these like agents who are sometimes competing, this is from the original Gann paper, where somehow the concept of Gann sprang full-grown from the forehead of Ian Goodfellow, and after a night of beers or something, whatever the legend is. So it's a min-max game. And so I was originally going to actually pick this math apart, but I don't think we're going to want to spend the time on that. But the point is actually it's not that hard. Basically, this equation is just like how good is the discriminator and how good is the generator. And you're basically trying to find a discriminator that makes this as big as possible. And so in machine learning, we're usually minimizing our objectives. So big is bad. So the discriminator is trying to make this loss as bad as possible, and then the generator is trying to make it as good as possible or as low as possible, and like for the worst possible D. And the idea is that like mathematically, we reach some sort of Nash equilibrium, and but I don't think we should dwell on that. But it's you can look at this purely from with a mathematical optimization perspective. This is the Gann algorithm from the original paper. I actually put it up here because I wanted to make a point that often these algorithms that they write into papers can be very kind of like included just because it felt like the right thing. But actually, if you look at Gann code, it looks like this. Like you really if you just read down your typical Gann training loop, it's like, we sample a mini batch of noise, and then we sample a mini batch of like real images from our data, and then we compute this gradient and take a step to update the discriminator. Usually this 4K steps is just one, so it's not even a loop. And the next one, we sample a mini batch of noise, and then we update the generator. And so if you were looking at papers and looking at code, they would look the same, and I think that's unusual and interesting. Okay, so this is like a different interpretation about what's going on in GANs, and I think as we piece these all together, I hope people will build their understanding. So on the left-hand side of this is if you've been taught about training neural networks, you've probably been taught about training classifiers and probably image classifiers. So this should be pretty standard over here. We have an image, it goes into some mysterious neural network that we don't need to talk about. Ultimately, it outputs class probabilities. So it says, oh, we think there's a 90% chance this is a dog and a 10% chance this is a cat. And we'd have some kind of a loss that tells the model how good those predictions were, and more importantly, allows us to backpropagate gradients to say, if you change the weights in this model, this would change your predictions for the better. And so we're able to build this machine that when we turn the crank on it, our model just gets better and better at doing classification. So in this little story I'm telling you right now, classifying images as being dogs or cats. And so that works great. wouldn't we like to do that maybe for generating dogs? Like, could we have this sort of like random noise and then some mysterious neural network that eventually creates a dog image, and then we have this thing that tells us like how good is the dog image, but more importantly, gives us gradients that tells us how we could update the weights in our generator to make it better at making dogs. And if we had this like mysterious dog loss, we could just turn that crank and train forever and then eventually have a great model. And the point I want to make is that basically that's what's happening in GANs. So it's like, this is what I had before, this is noise, this is generator, this is dog image, and then all of this is happening under the hood. So we have this discriminator network that's trying to predict if this photo is real or fake, and then we have some loss, which isn't always cross entropy, but for this purpose it will be. And so like, if you just took all of this and abstracted it out of the dotted lines, it looks like a loss function. It does exactly what we want it to do. It provides gradients to tell us if you change the weights in these ways, this dog image would get better. And so if you accept this like intuition, then instead of seeing it like as a competition, where when I'm training my discriminator, it's like getting better at beating the generator in this competition, whatever. Instead, I'm inclined to see it as like maintaining my loss function. I'm doing like loss function maintenance every time I'm kind of fixing this up. Because what I really want is I want it to continue giving me good gradients. Okay, so other things that are going on in generative modeling. This is another attempt to provide some intuition as to what's going on here. So on the left here, I have some data, okay? And it's like people, and it's their weight and their height in like pounds and inches. Why did you pick pounds and inches? Because I'm Canadian and it's complicated, okay? We have a weird relationship with metric. Anyways, so this data has like some distribution, and you might think to model it as like a two-variable Gaussian, multivariable Gaussian distribution. And so I don't need to train a neural network necessarily to sort of generate new people. I could just do this. So this is the code that I used, and I'm just sampling using NumPy to sample from a multivariate normal. These are their means, this is their covariance matrix, and I want 100 samples. And so in a sense, like that cell from a notebook is like, it's a generative model. It takes some kind of randomness. In this case, it's like randomness that came from the operating system or something. I don't know what the internals of NumPy look like there, but in any case, it takes some randomness and turns it into points. And this is a chart of the points that I generated, and the thing I want to say about them is individually, the points here could have come from that distribution. Like, so if you picked any one of them, you couldn't say this is fake or real. They individually, they look reasonable, and as a group, they look reasonable. This group looks like that group. It's kind of spread out along this diagonal. It has a certain variation. These points don't exist. These points don't exist. So both individually and as a group, they look the same. And so when we're training a generative model for dogs, we're kind of trying to do the same thing. So we're trying to create photos of dogs that individually look like these photos of dogs, and you couldn't necessarily tell which they come from, although I think we all agree you can tell in this case. Isn't that interesting? These are, again, top dogs, very good dogs. And we want them to somehow, as a group, look like this group. And so, like, somehow, if we could mathematically say whether or not this distribution looks like this distribution, and whether that pile of dogs looks like that pile of dogs. I shouldn't walk back and forth. It drives Bruce crazy. And I don't think I'm going to spend much time on this, but it's something I wanted to talk about. This doesn't flow very well, but that's fine. Gann training is notoriously difficult and unstable. Why is an interesting topic of research, and people do a lot of work to try and improve this. I pulled this, like, I think randomly from the internet just to make a point. This is kind of a typical, like, failed Gann training run where somehow, if we think of it, maybe we do think of it as a competition. What's happening is everything's going along hunky-dory. Generator's learning from the discriminator. Discriminator's learning from the generator. Everything's getting better all the time. That's great. And then something happens. Who knows what? Sometimes it's like numerical instabilities, or just why, like I said, it's complicated, and I don't pretend to understand all of it. But in any case, like things can collapse. And so in this case, what happens, and this is the typical kind of collapse that happens, all of a sudden the discriminator gets really good and too good. And every time an image shows up that's fake, it's just like obviously fake. And the generator asks, well, how could I improve this image? And like, you couldn't. Literally, like, none of these pixels matter. There's nothing you could ever change that would make this more believable. And so the generator, when it tries to, these gradients, like how could I update, change this, is meaningless. And so it fails, and then the discriminator gets better and better and better, and the generator just doesn't, and then you end up with nothing at the end. And so people do like a lot of engineering to try and reduce the chances of this. They make certain choices about loss functions. We'll touch on a little bit today. But that's the essential story of why training GANs is notoriously difficult. And the other one would be, because we're talking about evaluation. So like normally, if I'm training a classifier, and let's say the blue line is my classifier, my loss, maybe it bounces around at first because things are hard at first, and then it comes down nicely. This would be like a nice curve for training a classifier, and because this number is low, we would know that our classifier was good, like -1 in a bit. But in the case of generative adversarial networks, I mean, these are all just relative, right? Like this is basically just how good is the generator at fooling this discriminator. And so these numbers are kind of, they're not absolute and meaningful in any way. So like I could, like in here, the generator loss was going down, but that doesn't necessarily mean my dog images are getting a lot better. It just happens to be good at fooling this really stupid discriminator because it just got randomly initialized. So there's not a lot we can learn from looking at this information as to like whether or not we're succeeding. Okay, I'm going to keep trying to feed different sources of intuition and understanding to everyone. I have no idea if I'm succeeding. I'm not getting a lot of questions. It's a pretty bad sign. Okay, so I want to talk about like Gann problems. So if we were trying to create something that draws from a distribution, like what kind of failure modes might we meet? And so this is like a fake one-dimensional problem to try and give us some intuition about it. So I only have like 6 data points. These are them kind of laid out along a number line for x. And suppose there's like some true distribution. So if we had all of the samples and we built a histogram, it would be kind of shaped like this, right? And then we're trying to fit a model to this so that we can sample from it. And so what might go wrong? So one of the problems we have that we talk about is missing modes. And so the idea is that like my Gann ends up giving me some distribution where if I sample from it, I get points in here, and like I get more near the middle and fewer near the outside, but like I never get points from here and here. And so this would be like dog breeds that don't exist, or dogs that are never like upside down and looking cute at you, or something. They're in the real world, but they're missing. So this is something we want to worry about. Another thing we want to worry about is maybe like lack of diversity. And so we have these points here, and we know the true distribution, like it has, for example, there should be like some chance of getting points in this space, but our model doesn't give us any, maybe because there weren't any in its training data. So you have this sort of sampling error. And so like throughout here, you might get kind of too much probability density like in the places where you have data and not enough between. And so then a lack of diversity will mean that we have these kind of random dog images, but they all actually look like the same dog, like not just from the same breed, but actually maybe it's the same dog every time, and we don't get like the kind of variation you'd expect in real dogs. This one, I'd be happy to have anyone challenge me on these, because I struggle to properly differentiate this from the lack of diversity, and maybe the answer is that there is no difference. So mode collapse is a word that people use. They use it to sound fancy because it might be just the same thing as lack of diversity. And so here, I mean, it's essentially an extreme version of the same thing. Like, we only ever get samples from where we have like lots of data and we get nothing in between. Yes. Sorry. Well, are we even recording?
Okay. So with this mode collapse, it's compared to the last one, is there any sort of like hand-wavy type of example you can give that would explain the difference? I'm not really.
They may be different words for the same thing. I'd be open for anyone. Okay.
I have absolutely no background knowledge on this, so let that be forward. Could this just be interpreted as like overfitting the training set, sort of like just memorizing exactly?
That's my
those
next
points?
slide, actually.
Oh.
So yeah.
I'm not sure, but might it be that, for instance, sorry.
If you look at it, it'll have a green light. On the where?
Somewhere.
Just try to hang one at the top. The green light is on the side of the there. Okay.
It also fails sometimes. So.
Oh yeah, it turned off. So that was mine as well. So it might have run out of that.
What about now?
Oh, it's working right now.
Okay, so I might be wrong, but I thought that mod collapse could be, like for instance, with many digits, we have 10 classes, but for some reason our classifier, not classifier, generator generates only 0, 1, 2, 3, 4, 5, but never 6, 7, 8, 9, 10. So even there are like other modes in our distribution, like other areas where density function is high, we never actually generate from there. So in a sense, our generator prefers several modes out of many.
Yes.
Yeah. So this how. So in a sense, several modes collapse like 6, 7, 8, 9, 10. Like now not present in our data generator. So that's how. So that's different from previous, because in previous it's just we say that we observe only data which is highly likely. It doesn't matter from which mode, but here some modes just don't appear. Yeah.
Yes, and I don't know. Is there a microphone back there?
Hey, talking out of my butt here. If this is like a mini-max type problem, could it be that the generator has discovered like a dominating strategy over the discriminator?
So because we're continuously training these things, like I don't think that the generator ever kind of has such a dominant strategy over the discriminator, because we always get to train the discriminator more, right? And so if there's any kind of a signal there between real and fake, I think it has the ability to discover it. But I mean, it could we could have collapse of the competition in that way as well. Yeah.
Couldn't you have the case where you just don't have a very complex discriminator model and it's just not capable of learning?
Yeah, it could be underpowered. Yeah, that's true. And then you might never, like your generator won't be able to learn enough from it. Like that's a concern. And yeah, like so my next slide was like memorization. And so this would be a big concern because, I mean, basically, so going back to my previous thing, are these points individually convincing? Like, yes, any one of these points look like they came from the real distribution. As a group, do these points look like the real distribution? Also, yes. Is our model useful in any way? Absolutely not. And so, like, if you're generating dog images and you're learning from a data set, like coughing up that data set straight back again is a like really good way to create convincing images of dogs. And so if you're trying to run a competition with a leaderboard, that might be a problem.
Sorry, could I just go back to that?
Yeah.
Why doesn't the generator just do that all the time? Like, what prevents it from actually just spitting back out exactly the same image?
Just the difficulty of learning to do that. I think if you ran these things long enough with sufficient capacity and limited data and so on, I think they eventually would do that. Yeah.
Okay, sorry, hogging a little bit, but does that mean that early stopping is really important with GANs? Is early stopping even a thing with GANs?
You don't see it. I think the Gann research, the leading Gann research is done on like pretty hard problems. And so I think maybe you don't end up with sufficient capacity to memorize. But I would worry about it And so you'd want to do a validation, right, which would involve kind of computing these leaderboard metrics. Yes. Oh, yes.
So I have one question. In real life, how do you determine memorization is taking place? Like if you have a neural network, how can you debug that your network is memorizing versus?
So the competition metric has like an attempt at that, and I think like we'll see that in just a moment, and I think that'll be interesting. It'll get to your question.
Sorry, one point. If you get to a point where you're only generating these exact images, your discriminator model might not end up learning very well. It will just kind of also learn to memorize, and then maybe you can kind of have like a held out validation set of dogs that neither model sees, that you can kind of make sure your discriminator model hasn't just learned to memorize.
Yes, although I would, so yes, I mean, the essential machine learning empirical method would be to hold out data and do something with it. And so that will be the case. But I'll make the point that like the discriminator isn't real, like don't think of it as this like universally valuable, like real dog, fake dog, like critic. Like this discriminator only knows about images that came from this generator, right? And it's worse than that even because we're training it as we go. And so like as the generator evolves, the discriminator evolves. And so even a late stage discriminator might not be very good at discriminating images that were generated early in the process because it doesn't need to know that anymore. So it probably has a lot of forgetting. And so that it's not, I wouldn't use the discriminator for much at the end of training.
I'm probably missing something. How would it be able to memorize anything? Generator never sees a real picture. So generator just gets the noise. So and then this discriminator is just a loss function. There is no way it can memorize anything. It can memorize the distribution, but there is no way it can memorize the actual image. It's impossible.
Right. So okay. So when we generate images, well, this isn't a great slide for it, but like we sample from a latent space, right?
Yeah, you can go back to the initial model that you showed, and then there is no way you can memorize from that picture. Like it never sees that.
So yes, you can, and so the answer is that. So this is like a multidimensional vector space. And like what this model is learning to do is to map different regions of this space to like different dog images. And then when we would train it, the discriminator is essentially training it to make images that look like images in our data set and to essentially map this space to images that look closer to our data set. And so if you take that to the extreme, you essentially map regions to single points and to single images. And so it's not like direct memorization in the way like with a classification network, it's kind of more believable that the model would memorize the answer to the question. But I think it's very much possible in this case.
I think that the only possibility here is actually discriminator remembering the whole training set, and there you have the grab basically a loss function going into the directions. It's when, once again, discriminator remember everything in training set, and then there is no way for the generator to learn to actually generate real images. And that's why I don't think the overfitting for a generator is possible. Like there is no way. You can, again, get to the distribution, but not the image itself.
Okay, yeah, I'll stand. We can agree to disagree, but I will agree to say yes. So one of the things that could cause the collapse of this whole process, like one would be that the generator is just so crap that it gets useless feedback, but the other would be that the discriminator like just happens to memorize what is the training data, and then again, no improvement to the fake image would ever get anywhere because of that. Yes. Oh, you have a micro already, so we're good. Yeah.
I think that's a good segue. So what's the role of the random noise generator in all these different failure modes? Like if you just have like the same, if you fix the random noise to just the same vector every time, like wouldn't you have a perfect generator that be able to map out like the one of the images, or am I misunderstanding how?
So if you threw away all the randomness and it was the same input every time, then it would be deterministic output. And so you could ask the question, would the one generated image, because it's only ever going to be one, would it eventually look like exactly one of our training? And I think the answer is no, because the discriminator would be able to identify, oh yeah, this is the one image I see all the time. And so that one must be fake. And so the best you could possibly do with no randomness would be to somehow generate a mean image, right? Which is like kind of the average of all dogs, and that's not going to look like anything. And so I think you wouldn't, I think that would fail. And so that's why there needs to be this random sampling.
Okay, I have one more thing on the topic of how this generator can learn to memorize the images of the training set. And the way I think I might have it make sense in my head is the discriminator punishes it when it creates an image that doesn't look like one of the training images. And so if you do that enough times, you might eventually end up with an image that does look like one of those training images. Yeah?
Yeah.
Okay.
I mean, if I were teaching you to draw dogs, and I were giving you feedback based on a collection of drawings of dogs, I would probably eventually nudge you into drawing one that looks like one of the ones I have. It eventually gets there. And then, okay, so we're going to talk a little bit about 7:30. About how we measure these things. So this is a really popular Gann metric. It's called the Frechet Inception Distance, something like that. And so this is how it works. So if you're familiar with pre-trained models and stuff, you'll understand more of this. If you understand less, that's fine. We should be able to operate. So we take our real images and our generated images, and we put them into a pre-trained neural network. In this case, because it's the Inception Distance, for whatever reason, we just always use Inception v3, which is a particular ImageNet classifier. This has been pre-trained on ImageNet, so it's very good at predicting the 1,000 classes that images in ImageNet are. And it does something to the image to create 2,048 features. That's just a 2,048 dimensional vector where there's a number for every dimension. Then some more stuff happens and class probabilities come out. So that's what the ImageNet model does. We don't really care about this stuff. What we care is that at some point we have interesting features, 2,048. That, I mean, if it's as good at classifying images, then these features must contain interesting information about what's in the image. And so we can create a collection of these, one feature vector for every single real image and one for every single fake image. And so now we can ask, what is the distance between these two groups? Okay? And in this case, what's done is they're modeled as a multivariate Gaussian again. So we have 2,048 means, and we have a 2048 by 2048 covariance matrix. And then there are various ways that you can try and calculate that distance. This is it, okay, just written out. Why is this it is an interesting question. Having gone to the paper, I can tell you that these are essentially the first two terms in a set of polynomials. These are the first two moments. In practice, in theory, there are more. But in practice, it's feasible to just cut it short at this. So that's, and then once you see this type of shape with the 2, but square root and so on, you can imagine that. And then the other intuition that I just want to share would be, so if the means are the same, then this term goes to 0. And if the covariants are the same, then this is the same, so it becomes squared, which is square rooted, and it's just 2 of these minus 2, so this term goes to 0. So so you can, that's the basic, that's what we can walk away with from this. Yes, Matt. Microphone-less Matt.
Okay, I just want to make sure I have this right. So this is used after the actual training of the GAN itself, right?
Yes.
Okay, and I guess that answers my other question. The pre-trained model is completely frozen. There's no way to mess around with it?
Yeah, that's right. So
okay.
Yeah, we use this, and you probably want to do this on held out images, right? And this kind of a held out model in sense, so it's all clean. And we can ask the distribution of these features, is it the same, or how same is it to the real distribution? Yes. Also microphoneless. And probably a mat, but I don't know. And it's on, yes?
It's on. This is not for training, this is kind of like metric.
For evaluation.
For evaluation, okay, I see. And we train with that loss similar to one that you showed appeared in the first paper by young Goodfellow?
So
the ratio is.
So the loss function that you apply, you always apply it to the output of a discriminator, right? But sometimes it's to train a discriminator and sometimes it's to train the generator. And there are a lot of different choices there. And when we get to the winning solutions, I'll just talk about what a couple of those choices were. Like the obvious one is binary cross entropy, because like the discriminator is classifying, and so but there's like a lot of other choices people make.
And that one is not the best one.
Well, I mean, actually, interestingly, the winning solution used binary cross entropy, and that is very interesting because that goes against most best practices in Gann training. And so that's one of the values of looking at Kaggle competitions, is you see sometimes what the research would consider to be bad choices winning competitions, and that might tell us something about the difference between
that's interesting.
real
Thank you very much.
practice and research. So this is like, so if we had images, we could use this and compute this to compare. Yes? You're very quiet.
Is it on?
Yep.
It's on. So are we just using that network as a fancy encoder? I mean,
Yeah. Yeah, it's just something that takes images and turns them into numbers that are useful and meaningful.
and each is, okay.
And actually, there's all kinds of really interesting things you could do with that method.
So the 2048 features, are they 2048 for the real images and 2048 for the generated images, or?
Yes. Yeah. So if this magical box for somehow turns an image into 2048 numbers. And those numbers, if you inspected them in the right way, they somehow carry meaning as to what's in the image. They get used to do classification, so that it must be somehow carrying meaning. Yeah.
Hey.
So after observing this for a while, I think this is just a way of checking the distance between two distributions of real and fake. So you want to check the distance. So the inception is not important to this concept. This is just because for this competition, you could use any model.
Yeah, you could use any model, but you would need some kind of a model.
Yeah. Okay. Yeah. So I think this makes a lot of sense. Just from some linear algebra concept. I'll discuss that with you later.
Okay.
Yeah, my question is just, do people who compete in Kaggle make their discriminators with a Inception backbone? Does that seem to help at all, having a similar architecture to what the actual metric is going to be?
People don't do that, and I think the short answer would be that just doesn't fit on GPUs, because when you're doing this training, you're building kind of relatively large computational graphs compared to normal classification, and so the discriminators tend to look a little bit weak in their capacity compared to normal ImageNet classifiers. And then you had one more. You don't have a mic, but you could. Oh, there it is. Dangerously perched between two desks. There you go.
I wonder if instead of Inception, we would use some other popular networks and take, for instance, instead of this 2048 features, the last kind of pre-output layer of those network and then say we trained two generator and we want to compare them. Would this metric be consistent across different, this Fauché inception distances will be consistent across different architecture for feature extraction? My guess would be that not, but it's
I agree.
interesting
That's super interesting, and I would love to do a mini project to investigate that, or have someone else do it and tell me the results. So, those would both be great.
Yeah.
Is Kiri, you want to say something? Yeah, sure. You didn't put your hand up, but you looked at me.
I would probably add that it maybe not only depends on the architecture of the classifier, but also on the data that it's trained on too.
Yeah. Yeah. And I have a really juicy point about that we'll make sure we get in before the end. We're running to 8? Yeah? Yeah, okay.
Let's go up right until 8.
Yeah, okay. Okay, we'll see. Okay, so okay, if you're trying to run a competition with a leaderboard, and you're providing these images, you have this problem that people will just regurgitate the training images. And then when we do this Frichet Inception Distance, it'll be 0, and that'll be the best possible. And so what Kaggle implemented, they made this memorization-informed FID. And it's a bit strange to pick apart. I put all the equations on here. Essentially what they do is they take the generated images and they find the closest real image for all of them, okay? And then we ask, like on average, like that's what here is, like on average, what is the distance to the closest? And if it's too close, like cosine distance of less than 0.1, then we slap you with a big penalty. And so that's how they handled it. And I think it's very on-off. And I like kind of smoother penalties than that. But I think it was effective for their purposes.
Do you know what happens if you like rotate the image or just flip it horizontally? What happens to the cosine distance?
I don't know. Probably not a lot, given that these models are trained with those augmentations. I will say, though, I mean, the explicit rules of the competition were that you had to use Gann, basically, and that this was I didn't say these things earlier, but this was like a kernels competition. So you submit notebooks, and they run your code, and so everything was inspected, and illegal methods were disqualified ultimately. So that's another way you get around this, which is too bad because I think Kaggle would prefer something like more adversarial, where the players are trying to hack the competition and the competition organizers are trying to prevent that. I think that'd be more fun. But and life is complicated. So this is actually the flowchart. You don't actually need to read it. I'm just going to point out that there's this flowchart about how they're going to compute your score. And all these steps and arrows and stuff. The long and the short of it is that they had a public leaderboard and a private leaderboard. Where the public one, they used Inception v3, probably the TensorFlow one, which is considered the standard for this metric, and they used the Stanford dogs. But then for the private leaderboard, they have this mysterious pre-trained network, something else that might be generating like slightly different features, but maybe is somehow less subvertible, and some like other photos of dogs so that no one else has access to, so that you can't kind of game that. And so I think that's what they constructed in order to get around that. Here's what the leaderboard looked like at the end of the competition. So the winning scores were like whatever, 55, 56, fine. Comments, lots of solo competitors, which I think is kind of unusual, but maybe that's because it's a notebook, so you don't get to do an ensemble. There's no ensembling, so there's not that push for groups. I think maybe what's interesting about this leaderboard is this. So what's going on here? Why? So this is, so for those of you who don't know, Tom finished first. And the difference between the private leaderboard and the public leaderboard was that he went up 438 points, places, which is like half of all teams. So what's going on there? The answer basically is that a bunch of people were like openly cheating in their notebooks and creating illegal solutions that scored high on the public leaderboard, but were then later basically disqualified with 99999 as their score or something. So a whole group of people just got dumped below the line, but like openly cheating rather than privately cheating. So it wasn't not so bad, right? Okay, so let's just talk about the first place solution. I'm just going to go over some choices they made. Feel free to ask some questions. So some of these things are interesting. So okay, something that everyone did. I think this is very common. So preprocessing and augmentations. We've got these photos of dogs. Like we have a bounding box, as I said earlier, so we know where in the photo the dog is, and these dogs are in like exotic contexts. And so if we want to generate 64 by 64 images of dogs, and by the way, that's the resolution we're talking about here, that's why the dogs all look kind of crappy, like you're probably going to want to isolate the dog in the photo. Because if you just take this photo that's like got a couch and a dog in it, and then shrink it down to 64 by 64, like you can barely see the dog. And so they have this process of throwing away dogs with weird aspect ratios, throwing away images with intruders. Someone did some analysis where basically images that didn't just contain like a single dog, so that might be pretty confusing. You know, dogs with multiple heads might become a problem if I've got multiple heads in my training data. Using the bounding boxes to cut out the dogs, resizing things down to 64, and then of course they horizontally flip these dogs. But we don't vertically flip dogs because dogs have a certain orientation. This person used Big Gann to give you a sense of size of these things, by the way. He reports that his generator had 10 million parameters in discriminator 8, which if you're new to computer vision with neural networks is a big number, but if you've actually looked at ImageNet models, those are small numbers. That's interesting. He drew his sample noise from a normal distribution, 120 dimensions. This is an interesting point here. So I think in the original Big Gann, they used ReLUs, but when he implemented it, he uses leaky ReLUs. This is an example of the kind of choices that people make to attempt to stabilize training. So we won't actually explain that. If you know what leaky ReLUs are, then fine, you'll understand maybe why you just get more gradients out of leaky ReLUs. They don't saturate at the negative. He used the truncated trick or truncation trick. Basically, what people have discovered is when you're sampling data from this normal distribution, you tend to get like sometimes data from the tails. And those tails tend not to give like great photos. And so if you just artificially chop off the tails, truncate the normal, you get like better samples. It's not like very satisfying mathematically because like those tails like should be representing something, but like empirically you get better FID scores. So even researchers are doing that. This person didn't use exponential moving average, but the second place solution did, which is why I mention it. This is where essentially you keep track of a smoothed copy of your model as you train it. And then when you're done, that's somehow better than this one that bumped along during the training process. Everyone used this thing called auxiliary classifier Gann. So essentially, they don't just sample random dogs, but they actually bake the dog breeds into the process. And so like when the generator is asked to generate an image, it's told what breed to make. And it's also told to like convince the discriminator that's also classifying breeds that it is the breed that it was told to create. And so that's where you get better structure. We had hands in the air over here. People with microphones can talk if they don't.
Thank you. My question is about background. I understand that they cut the bounding boxes, but there is still background in the bounding box a little bit, right? So did anybody try to get rid of the background? And
no, people just took the stuff straight, yeah.
Okay. Do you think that, like you were just talking about tails and background, I think it presents more kind of noise. So if you want to generate dogs, you should probably do it without background.
Yeah, I agree. I think for practical purposes, it's good to kind of throw away the background so you can just focus on the dogs. I agree that there's more variation in dog context than there is in dog, because there's only so much dog in this world that they could be anywhere. But I do think if you wanted to ultimately do this job like perfectly, then you would want to sort of have dogs in grass and dogs on couches and so on. But I think that's too ambitious. So, yeah. Yeah. And, always.
I have a question about distribution of noise. Is it standard practice to use normal distribution, or could it be like uniform distribution or some other distribution?
I think it's typical standard process to use the normal distribution.
And do you know why they use it?
I will say I think it's the second place solution actually used uniform, which I think is interesting. Why? Like in principle, I don't think it matters, but everyone likes to feed Gaussians to neural networks.
Okay, so but Gaussian and uniform both work basically.
I think so.
Okay,
yeah.
cool. And and also I had a question about the number of parameters. Is there any like dependency between how many parameters a generator has and discriminator has? Like, can it be like on the like 1,000 times more parameters in generators and discriminators stuff like that?
Machine learning alchemy would suggest that they should be roughly balanced. And I guess that's generally considered to be true. But yeah, I don't think there's, I mean, if you could run the experiments and demonstrate that a different ratio worked better, then we would all accept it.
Have you heard that people discussing these sort of things? Discussed or not really?
I've researched a little bit about it, and you get basically that. You get this like, oh, they should be balanced because that feels good. And it works, it seems. But yeah.
Oh, okay, thank you.
And then, yeah, so the thing I wanted to emphasize about the winning solution was they use this binary cross-entropy loss. And like I said, that goes against, I mean, so we like using this loss for classification because when we're really wrong, it gives us like really big gradients. And so that helps us avoid these really wrong cases and leads to good outcomes. However, if we want this optimization, this min-max game, this competition to be stable, when you throw in big gradients, maybe things just suddenly skip off in a new direction and everything collapses unexpectedly. And so generally people avoid that. Now, like this first place solution is not necessarily like, this isn't state of the art for generating dogs. This was, using Kaggle kernels in 6 hours of time using the Stanford dog data set. And so like, there's a difference between the methods you might use. But I think it's very interesting that this was the first place and that they made that choice. Yes?
I'd like to go back to a number of parameters. And I was thinking about that back then. You discussed the collapse of the training. Did anybody try? I mean, does it work when you do the generator like has, let's say, 2-3 times more parameters than discriminator? So basically make discriminator weaker on purpose so it doesn't collapse.
Yeah, I mean, I think you can, you end up with a generator that doesn't learn fast enough, and then you wait for all of time for your whole process to converge on good images. That's like the downside of not having a good enough discriminator, is you're not like learning useful signal to train on. So that's the trade-off, I think. So it's probably more stable, but slower, essentially.
Okay, thanks.
Kiri has maybe a better answer.
I think if you're going to put more parameters in one of the generator or the discriminator, you should put more parameters in the generator because the generator, I think, has the harder task. It has to always, if you give it a little bit of extra capacity to try to fool the discriminator, that's going to help the generator.
I think it's very reasonable. And then, I don't know, I think this label smoothing is another choice. It's if you know what that means. I mean, it's the kind of thing we do training in classifiers, and it's the kind of thing that would smooth your gradients. So that's interesting. And then this second place position actually had an embedding for their breeds. So they took the 128 possible breeds, then pulled up a feature vector for each one. And then interestingly, they did use one of these more exotic choices, not one of these different choices you might make. Actually, I do think it's somewhat exotic for their loss function. This is like it if you wanted to read the PyTorch, and I encourage you to use PyTorch. But essentially, what I believe the loss is if we ignore the margin, we're taking the average of all of the real probabilities and the average of all the fake probabilities and trying to push them apart proportional to their squared difference, which doesn't look like binary cross-entropy at all, but gives you interesting gradients. Yes, Ken?
Yeah, is there a link between GANs and SVMs, like the support vectors, because the margin stuff? Is there a link?
No idea.
Okay.
I don't know where to begin with that question, but if anyone else does.
So I was saying, is there a link between like GANs and SVMs, the support vectors, those margin stuff? So because it seems like there could be a link between both. Yeah, but I don't know.
I do think some of these losses look kind of like margin maximizing losses. So there's maybe something going on there. Kiri has a point.
If you look at where losses come from, they frequently come from KL divergences. So if you definitely binary cross entropy comes from a KL divergence, and if you start to look at arguments for where does a loss come from, it may start with a KL divergence.
This is just fun for a moment. So common prohibited methods. So things you weren't allowed to do, but people did. So for one, this was essentially where the big leaderboard shakeup came from. People invented this memorization Gann. So they train the discriminator a whole bunch and then freeze it, and then train the generator. And this doesn't exactly memorize the data, but it did it well enough to fool the public leaderboard. So a lot of people were doing that. Some people were attempting to map this one hot encoded vector to every single training image, and then just train a model to generate those on demand. Some people used variational autoencoders, which is actually not prohibited in itself. But the training of those essentially involves like taking an image and turning it into this kind of number in the latent space, and then turning that back into an image. And so this, if you do that to create your dogs, then you are basically just modifying the original dogs. And so that's not that interesting. And so and then essentially you might be doing what this last point was. I guess people actually did attempt to like rotate dogs, flip dogs, blur them a little, somehow create convincing new photos of dogs that are not really all that new. I put this in my presentation. So I think this post aged really well. So this is early on in the competition, and Pavel here is complaining. He's complaining that this competition is too easy to hack. People are already doing it. And we're going to spend the rest of time discussing what's legal and what's not. And the reason why this is interesting is because Pavel used to be a Kaggle grandmaster, but he got banned because he got caught cheating. He actually won. He cheated. He won a competition. He received prize money, and then eventually they found out. So I just thought that was like fun when I found that in the discussion section. And then finally, yeah, I wanted to also shout out to 6th place, because they didn't use big Gann, they actually used progressive Gann. And to give you a sense of what that is, these are actually photos from his notebook of the Gann training. And so the strategy, the idea is that learning to generate these 64 by 64 dogs right out of the start is just hard. Like, there's lots of detail in there. The discriminator is going to figure out that you're not good at detail, and it's just going to give you shitty feedback. And so what you might do instead is you start with this kind of low resolution. And so if you can just convincingly create like blurry dogs, and then once we get sort of something stable there, we up the resolution. We essentially, you add a block to the generator so it can go double, and you add a block to the discriminator so it can handle double, and then you transition to this new resolution. And so you build it up. And this has been shown to be like a good way to create these good high-resolution images with detail. I believe the original StyleGAN was trained in this way. I think they actually may have dropped it from StyleGAN 2 because they found it generated artifacts. Because you can imagine, like, if you trained your model in this exact way, then like my high-resolution model was like, it has some kind of like history of having created things that only had to be blurry or something. It's kind of hard to, if you looked at the StyleGAN 2 paper, you'd find some kind of analysis they did where they found artifacts that came from that. You look like you have a question. Yeah.
So we saw the previous guy cheating, and I'm looking at the private and public leaderboards. The private ones are the ones that follow the rules. They did what was expected, and it worked for Kaggle and to win a competition at Kaggle. Now I'm here to learn about Kaggle, but also importantly to be able to apply this in whatever field I go out and do that. As a learning experience, is it sometimes good to go and check out the public leaderboards that may have not followed the Kaggle rules, but that may resemble more of like real world, or is it just better to stick with, I don't know, the constraints of the competitions?
So this is unusual. For the most part, Kaggle competitions never contain a rule that says what method you're allowed to use. This is the only one I know of, so that makes it very unusual. And then other forms of cheating are also like extremely rare. Okay. And so broadly speaking, yes, the public leaderboard is very informative. Yeah. And then I had these two like final questions that really make me kind of wonder, actually, about the competition. So these Stanford dogs, I tried to figure out exactly where they came from. I think they're actually photos from ImageNet. that they post-processed with bounding boxes and breeds and stuff. And so, like, if this model they used for FID was trained on ImageNet, then it's been trained like on those photos of dogs. And I mean, what might that do to those 2,048 features? Like, we know, for example, that the model it's spuriously good at classifying those images because it was trained on them. That's why we hold out data when we want to know how good a model is at making predictions, because we know it's overly good at the data we trained it on. And so therefore, I feel like probably those 2,048 features are somehow invalid if we used a model that was trained on them. And so we might also ask, like, what about the mysterious dogs, the ones they use for the private leaderboard? And so is that something very interesting going on between public and private? And then the other thing that I thought was interesting, I mean, at this point is about sort of, I wrote it for MFID, memorized informed FID, but broadly, I do think it's interesting that all the competitors use the bounding boxes to cut down the dogs to just have a dog for their generator. But all of the metrics were computed on not cropped images, right? And so that's very interesting. I mean, for one, you would think that that gives you an opportunity to increase your score, because grass and couches are going to show up in these images, and they're not going to show up in what you generate. And so I also would really wonder about the public dog images and the private dog images as well. Like, given that these bounding box cropped dogs did so well, does that mean that the private images are perhaps cropped or zoomed in? Or, I mean, for sure the private images come from a different distribution than the public images. And I mean that in, like, I'm waving my hands because it's some kind of hand-wavy way. Like, they didn't come from the same place, so they're going to look different somehow. That's always true. So those are my thoughts, especially the first one, to debate over beer. And that's my last slide.